Hello and welcome to all students. This is FY semester 2nd class, paper 1 calculus 2nd, unit number 2 differentiability of functions. Today in this lecture we discuss about and differentiability of function. Continuity and differentiability of function. So let us prove one theorem. The statement of the theorem is, so let us write the theorem. So statement of the theorem is, if f from I to R is a function, is a differentiable function, is a differentiable function, at point P belongs to I, at point P in I, then f is continuous, at point P. Continuous at point P. Okay, so let's try to prove this theorem. Proof of the theorem. See here. So read that theorem once again. Theorem says that if f is a function from I to R, which is differentiable function at point P in I, then function is continuous at point P. In other words, if f is differentiable at point P, then that function f is continuous at point P. That is the theorem which we have to prove. Okay, so proof is very simple. First of all, we write what is given to you. Given f is differentiable at point P. Okay, therefore by definition derivative of function f at point P exists, that is the limit as x tends to P of f of x minus f of p whole divided by x minus p exist. Okay, so this is the meaning of differentiability of a function. Okay, now what we have to prove is, we show that f is continuous at x is equal to p. So that is, we show this equality, limit of f of x as x tends to p is same as f of p. Okay, so this is the definition of continuity. We have to show this equality. Okay, we show this equality. So let us consider now. Consider consider the limit of f of x minus f of p as x tends to p. Okay, consider this limit. On the next line we make some adjustment. Limit x tends to p. For this term f of x minus f of p, we divide by x minus p and then we multiply by x minus p. See here, divide by x minus p and multiply by x minus p. Now we take a separate the limit for these two terms. In the next line we write it is equal to the limit of this quantity, limit x tends to p of the function f of x minus f of p and whole divided by x minus p into limit x tends to p of x minus p. Okay, it is equal to the value of this limit exists and the value is derivative of function f at point p into the value of this limit is 0 and 0 into this derivative is equal to 0. Okay, so what we have, the value of this limit is equal to 0. That is, we write that is the value of limit f of x minus f of p as x tends to p is equal to 0, and therefore finally what we have is limit x tends to p of the function f of x is equal to f of p, and this shows that function f is continuous. Function f is continuous at x is equal to p. So the proof of this theorem is over. Okay, so this theorem says that every differentiable function is continuous. Okay, so we write here remark is every differentiable function is continuous. Okay. Every differentiable function is continuous, but we say that if function is differentiable then it is continuous. Okay, but the converse of this theorem is not true. So this is our first remark. Second remark is the converse of this theorem is not true. Means every continuous function is not differentiable, or every continuous function may not be differentiable. That is, every continuous function may not be differentiable. May not be differentiable. For example, consider the function f of x is equal to mod x function, and it is defined for all real numbers. Okay, and we know that the graph of this function is, we try to draw the graph of this function. Okay, here we will draw, suppose this is our x-axis, and now we have y-axis. Okay, and the graph of mod x function is here. Okay, okay, mod x function. Okay, you see here this function, so it is x-axis, y-axis, perpendicular, origin. So this is the graph of the function. Okay, now this function is continuous at all points, but it is not differentiable at x is equal to 0. Okay, so this function is continuous at every point in R, but it is not differentiable at this corner point. Okay, mod x function, mod x is continuous on R, but or continuous, I will write here now one thing, continuous on R, obviously it is continuous at 0. Okay, mod x is continuous on R, therefore it is continuous at 0, but it is not differentiable at 0. Okay, but it is not differentiable at 0. So this is the best example which shows that the converse of above theorem is not true. Okay, the converse of above theorem is not true. Let us see some examples now. So consider, main question is show that the following functions are not differentiable at the point mentioned against them. Show that the following functions are not differentiable. Show that function is not differentiable at point mentioned against them. Okay, so let us take first function. That function is f of x is equal to 1 when x is a rational number, and it is equal to -1 when x belongs to r minus q, means x is irrational number, and we have to check the continuity or differentiability of that function. We have to check the differentiability of that function on entire R. Okay, on entire set of real numbers. Okay, so we write the answer for this question. So we know that this function is nowhere continuous function. This function is not continuous at single point in R. Therefore, this function is not differentiable. Okay. So this function is not differentiable. Not continuous implies not differentiable. Okay. So we write here this function is discontinuous at every point in R. Okay, therefore this function is not differentiable. Function is not differentiable at any point in R. Okay, over and out. So this is about the first example. Now let us go to the second function. Is, see here, f of x is equal to greatest integer function. X is greater equal 0, less equal 2. Okay, and we have to check the continuity at or differentiability at 1 and 2. So let us write the answer of this also. Now we write that function f of x in detail. So as it is greatest integer function, so in case of when x is greater than or equal to 0 and strictly less than 1, in this case that function must have value 1. Sorry, it is not greatest integer function, it is a step function, and in this case the function has value 0. Okay, now in second case, when x is greater equal 1 strictly less than 2, then function has value 1, and when x is equal to 2, then function has value 2. So this is a step function. This is a step function, and we know the graph of step function. Okay, so let us try to draw the graph of this step function. So this is our x-axis, y-axis, perpendicular origin, 1 2, here is 1 2. Okay, so in this range, when x is in between 0 and 1, function has value 0. So our first graph is on this line. So our graph is here. Okay, now when our function is in this range, 1 minute, there is no touch to 1. Okay, now when our function is in this range 1 to 2, the function has graph 1, function has value 1, means our graph is like this. Okay, okay, and when function has value 2, when x is equal to function has value 2, you see here, the function is discontinuous at x is equal to 1, x is equal to 2. Therefore function is not differentiable at x is equal to 1 and 2. Okay, there are 2 points of discontinuities, 1 and 2. Function is not continuous, not differentiable. Okay, similarly I would like to give homework to you to check the differentiability of functions. Okay, so let us write homework. So check the differentiability of these functions. First function is f of x is equal to 1 upon x, and when x is not equal to 0, and it is equal to 1 when x is equal to 0. So we have to check the differentiability at x is equal to 0. Now second function is f of x is equal to sine 1 upon x when x is not equal to 0, and it is equal to 1 when x is equal to 0, and we have to check the differentiability at x is equal to 0. Okay, these are the two homework for you, and let us stop this lecture. This is the end of this lecture, and thank you for paying attention. Thank you very much.